Welcome to this lecture on pre-processing of remote sensing images, satellite images, basically. The focus of this lecture is actually going to really be on Landsat type, Sentinel-2, Landsat 8-9 type sensors, rather than, say, radar or anything like that. So what is pre-processing? Well, as the name might imply, it's processing that we do prior to the other things. Basically, what we have to do is get our data into shape. We need to correct for the real world. We have light coming from the sun, hitting the Earth after passing through the atmosphere, going through the atmosphere, hitting the Earth, then going through the atmosphere again and going back and going out to a satellite. So lots of things are happening, which makes the whole thing a bit messy, and we need to try and deal with some of that mess. And that's what pre-processing is, what we need to do with the data before we can actually start doing our image classification and that sort of thing. But just before you get too despondent, quite often data is provided ready processed for us, nowadays especially. And for a lot of these simpler tasks, that's fine. We can just use that data. But if we're not happy with that, what do we do? Or what has happened to this data that we have received that has been pre-processed for us? So what is this pre-processing? If we look here, this is NASA's description of the different levels of pre-processing that it has. So level 0, stuff you're really actually not going to get hold of. What you're likely to get hold of maybe is the level 1A and 1B. Whereby you've got some adjustments for radiometric effects and the geometric effects. Not everything has been done, but some of it has been done. Then we got this level 1B, which is slightly more processed. There are different degrees to which we can go. Not everything is processed up to all these levels. And then once we start getting above this, according to their schema, we get level 2, where we're actually looking at stuff that isn't the spectral data that is actually being measured but derived from products, something else. So here we're fully processed beyond beyond the spectral. What then are we talking about? So let's get some get some terminology sorted out. Radiance. So this is the light that is actually measured. The strength of the signal, watts per square meter. That's regardless of where we're measuring. That's just what radiance is. Reflectance is a ratio. It's unitless because it's a measurement of how much of the incoming radiance is reflected back. So we're dividing one by the other, so there is no units. It's just a percentage. How much of the incoming radiation is being reflected out again. At sensor will refer to a measurement made at the sensor, in the camera, as it were, entirely uncorrected. Top of atmosphere. Again, this is fairly. What seems almost fairly self-explanatory, something at the top of the atmosphere. Typically, this might mean the signal leaving the top of the atmosphere. So it's already passed through the atmosphere twice, so one's going down and one's coming up. But it depends on what we're looking at. So top of atmosphere just simply refers to that place. But what it might mean, top of atmosphere reflection or radiance or these different, depending on what other word is used with it. But that's what it's referring to. And bottom of atmosphere is, generally speaking, the signal at the ground, the thing that's of interest in a lot of cases. If you're an atmospheric scientist looking at what's in the atmosphere, the bottom of the atmosphere isn't the most important. It's certainly important in terms of your analysis, but maybe you're interested in what's happening, the messy bit in between. You're interested in the mess, whereas others are interested in getting rid of the mess and looking at the ground. A couple of other words that are quite important here. Scene typically is the area that is being measured or surveyed, or the image has been taken over a particular area, and these tend to be fairly standardized. So one sensor, Landsat 8, 9, or Sentinel-2, whatever it is, will repeatedly deliver a product that covers the same area, has the same footprint on the ground, and that's a scene. Whereas an image is both that scene and a particular time point. So when was that image taken as well? So the scene just describes where we are, whereas the image is the where and when. So we know that it's this particular scene taken at a particular time. So if we want to do look and change detection and things like this, we can get different images of the same scene. So what's all that about? What does it all mean, really? Well, if we consider what we actually have, we have the sun illuminating the Earth through the atmosphere, and then that light being reflected back from the Earth up to our sensor, a satellite. And of course, this is entirely not to scale at all in any way whatsoever, but that just illustrates the basic point. So if we start thinking about the signal that's coming in, we're measuring a real-world signal. The incoming radiance at the sensor is an analog signal, as it were, depending on, we have this wave coming in, and we need to measure it. So we have a sensor that is looking at this signal, and it's being measured coming in, and the strength of that signal, an analog signal, needs to then be converted into a digital number. We need to store it on a computer. So it gets converted to our digital number in some manner at the sensor. We already here have problems. We need to determine what strength of signal corresponds to what number. So what does 0 mean? What does 255 or 4096 mean, depending on how many bits we have for storage? We also need to consider whether our sensitivity is linear as well. Do we linearly have different steps of intensity going up in our digital number? This is obviously the sensor itself determines a lot of this. In fact, all of it essentially. So we need to have that well calibrated in order to understand how our sensor is going to be reacting to different levels of light coming in. And to know this, because of course all instruments degrade and change with time, we need to be able to calibrate this in some manner using some sort of absolute value. Now we might have a known source emitting light. We might be able to close off our sensor and just have a dark space. We might be able to just point our sensor at open space and hope that it's dark, or point it at some known light source and say this is the maximum, or this is a particular strength of light without the atmosphere affecting it. Pointing at the sun is probably not a great idea, but pointing at some other luminous feature might help. Or we generate a signal ourselves within the satellite. So this is needed to be done in order to know what the digital number actually should represent.